Alrighty, hello there guys. Today is going to be a quick practice of the kinematics equations that you were introduced to last time. This is going to be awesome. This is going to show you, whoops, it was so awesome I threw my pen. This is going to show you how you put those equations to use. So you have to know these equations, and even though they might not be dripping off your tongue yet, let's put them on a cheat sheet, something like this. Keep all of these important things in front of you, and let's do a couple questions. We only have 2 questions in today's homework. I'm going to do one, and then you're going to do one. So it'll be like, me do one, you see one, then you do one, and I'll see what you do. Pretty cool, huh? Okay. First of all, I want you to know I'm writing a book about all the things I should be doing in my life. It's an autobiography. Yeah, an autobiography. Okay, I know. I'll stick with physics. Alrighty. So, just a quick reminder of these 4 kinematic equations. They all are different because they have something that they leave out. The first one leaves out distance, the second one leaves out acceleration, the third one leaves out final velocity, but you do have a v sub 0. That means initial velocity is in there. And the last one has no mention of time, and so if your problem doesn't mention time, then that's the one to pick. Also, one more thing that you need to have dripping off your tongues. If the acceleration is due to gravity, then A is the same as G, which is 9.8 meters per second squared. So anytime you drop something from an airplane, it falls to the ground and it's accelerating because of gravity, or even if you throw something upwards in the air, it's still accelerating towards the earth because it's going to slow down as it goes up. It's going to increase in velocity as it comes back down, and that's all due to the acceleration from gravity. Alrighty, let's jump into this first problem, which is about a penny. And in fact, what happens when you drop a penny off a building? Well, we shall find out. Today it says a 10-gram penny, so that's the weight of the penny, we'll talk about this in a second, is dropped from a building that is 125 meters high. The penny is initially at rest. Approximately how long does it take the penny to hit the ground? Okay, now this problem does what a lot of those tricky test makers do, which is something you are not going to be falling for, is they give us information that we don't need. Do we care how much that penny weighs? We do not care. It could be a penny, it could be a feather, it could be a hammer. You watched that experiment, the famous one that they did on the moon where they dropped a feather and a hammer at the same time. It both hit the ground at the same time. Doesn't matter how much it weighs. They accelerate towards the ground at the same rate. Now, of course, when you drop a feather and you're actually on the earth and you have atmosphere, there's going to be friction that's caused by the air on a feather, and that plays into it. But let's say if you took things with the same amount of friction, like a heavy bowling ball and a light bowling ball, they would actually fall at the same rate. That was discovered a long time ago. So we don't care how much the penny weighs, but what do we care about? We care that the building is 125 meters high, because this is going to be the change in distance. Sweet. We also care that the penny is initially at rest, because this is going to be v sub 0, which is going to be equal to 0. Approximately how long? We do care that they're asking how long, because this implies time. We're going to have an equation that says time in it. And that's about it. So let's look. Sometimes I like to put all the variables that could be mentioned right there in a row, and let's fill in what we know. All right, so we know that the change in x, or the change in distance, is 125 meters. This is also a good place for you to check and make sure that all your units are compatible with each other. You don't want to have feet for acceleration and then meters in your distance. That would give you an answer that is wrong. So make sure that they're all compatible with each other. V sub 0, it's starting out at 0 meters per second. So we know that. Final velocity, what do we know about that? We don't know nothing. It doesn't tell us final velocity. It doesn't ask us for final velocity. So therefore, that's not really going to be a part of this problem. What about acceleration? Now we know that this penny is free falling, so the acceleration is going to be equal to g, which is equal to 9.8 meters per second squared. Those are the units that you use for acceleration due to gravity. Time is our unknown. I'm going to put a question mark there, but we do want that to be part of the equation. So which equation is that going to be? Let's look at our cheat sheet again. When we don't know anything about that final velocity, we know we're going to be using equation number 3. Sweet, easy peasy. So I'm going to write down that equation. The first step when I'm answering questions like this is to choose the right equation and then write it down. V sub OT plus 1/2 AT squared. And in this situation, we are going to be solving for the unit t, and there's actually 2 unit t's, so sometimes these can get a little tricky just based on the math. But as you'll see, this one will simplify, so it'll be okay. All right, let's start filling in what we know. So for this delta x, I'm going to put in 125 meters. So I'll do 125 meters is equal to V sub O. V sub O was 0 meters per second. So look what's going to happen. I have 0 meters per second times t. That whole term is going to cancel out. So I'm just going to get rid of it now because it just turned to 0. And 0 plus this other stuff is just going to leave that other stuff. So I'm just going to put 1/2 A, which is 9.8 meters per second squared, and t squared. Alrighty, now we need to solve for t. So let's start simplifying this. The first thing we can simplify is what's 1/2 of that. So let's leave this the same. 125 meters is equal to 1/2 of, and what they did when they did this problem, because they wanted to know approximately what is the time, they rounded this to 10. So let's just do that just because we're approximating. So if we round this to 10, half of 10 is going to be 5 meters per second squared times time squared. Alrighty, now I want to isolate my variable. So I'm going to divide this by 5 meters per second squared. But instead of having a fraction on top of a fraction, what really happens, if you remember, is that this goes on top. Okay. So does that make sense? When you're dividing by 5 meters per second squared, because I want to, what I'm actually doing is dividing both sides by 5 meters per second squared, because you can do the same thing to both sides of an equation. That cancels out. Let me just, that cancels out. And then when I put 5 meters per second squared on the left side over here, I could write 5 meters per second squared, but it's a fraction on top of a fraction, so I just bring that on top. Does that make sense? Tell me if it doesn't make sense. Anyway, what happens when we do this? Okay, this turns out pretty cool because now we have 125 divided by 5. What is that? 125 divided by 5 is equal to 25. So let's simplify this to 25. And did you notice that the meters canceled out? There was meters on top, meters on bottom. That cancels out. Okay, so now the only thing we have on this side is 25 seconds squared. I just want to bring that over here. That's all I want to do. Those are the units. 25 seconds squared, I'm going to clean this up a little, is equal to, all of this cancels out, makes it a 1, is equal to time squared. Did you follow how I did that? Okay, now I don't want time squared, so I want to square root both sides. And then I'm going to be left with time is equal to 5 seconds. Sweet, that's the answer. All right, tell me if there's any part of that we did not follow along. And here is problem 2. So the famous saying, you're going to see one, and now you're going to do one. So this is the problem that you are going to do. I will get you going. And then let's see how you do. You will text me the answer when you're done with this. So we have a car in a drag race started from rest. So what is that telling us so far? We know that v sub 0 is 0. And it accelerated constantly. Okay, it accelerated constantly. That's fine. That's just telling us that we can use these kinematic equations because these kinematics are valid whenever there is constant acceleration. So it's kind of giving us a hint that we're on the right track. So it accelerated constantly to a velocity of 50 meters per second. Ooh, that sounds like it's going to be the final velocity. So I'm going to put v here, 50 meters per second. When it reached the end of a 500-meter road. So that's telling us the distance, 500 meters. What was the car's rate of acceleration? Ooh, they want to know A. They want to know A right there. And does it say anything about time? No, it doesn't. So that is not asked as part of the equation. So let's look at our kinematics equations. This one, number 4, is the one that we're going to use when we don't know anything about time. I'm going to copy this. I'm going to bring it down here. I'm going to use my little cheat sheet. Okay. I made my cheat sheet a little dirty, but it's okay. So we are going to use this equation 4 because we don't know anything about time. V squared, now that's going to be your final velocity, is your initial velocity squared plus 2 times your acceleration times the total distance that you traveled. Okay? And what are we solving for? We are solving for this variable here. So you figure this out. You tell me which one it is. Text me the answer, okay? And we'll go over it. Sweet. Good luck with that. And guess what? I'm a proud mom. Even if I'm not your mom, I'm a proud bonus physics mom. Alrighty. Still proud of you. I can still be proud. All right. Good luck. Bye.